kind of plants. And there's not much room. They're about, I would say, 7 foot by 7 foot diameter holes, kind of thing, little crawlways. The pipes are stacked on the walls, both sides. All your utilities and steam lines, water lines, gas lines, they all go in parallel. So there's not much room. So what you do is you let them, just like we saw before, straight run. Here they will do this trick here. They'll put anchor here in the straight, if the straight line, they'll put anchor here, put expansion joint in the middle. So there it helps to have in the middle because you want to take care of the whole length of the pipe in one direction. So it depends on your, where you want to need them. So these are different types of applications. You know, if you got this pipe growing this way and that growing that way, so if you have only one here, it will tear it. It will shear that. You got a lateral movement. So they got universal tied joints here. They can take, this can take care of this guy, this can take care of this guy. So it's a combination of two. This is untied, this is tied here. Same scenario, different applications can take offsets, yes. That's how it looks like. So just different applications depending on what kind of needs you have. Now this tells you how a bellow works. This is the basic principle of this one here is there is axial force here. That's what going, if this is your lateral, this is your angular. But this pressure thrust here we are talking about, or the blow apart pressure forces we're talking about, is illustrated right here. Because the force depends on that your pressure into the area inside the pipe. So that's how they calculate there the forces here. That if you guys have, I don't think you can read that. Slide is too small on your handouts. But here is that they have calculated it. Here shows how many pounds the thrust force will be. What they got. So you guys can, if we got a chance, you guys can look at that one there. Okay, so now we know how we can achieve the flexibility in the system. So that's all we talked about with the bends, offsets, expansion loop, or the expansion joint. You guys seen the application and you see how they look like. Now, what we're going to do again is still the pipe stress analysis. We still haven't gotten into the pipe stress analysis. That's what we started with. This class is about pipe stress analysis. Okay, now we know all the things available to us. We know how they look like. Now I say, okay, now I'm ready to do the stress analysis. Okay, what do I need? So there we have to, the pipe stress engineer has to sit down together, collect all the information. So I want to look just like the how much flexibility is required. You can't have way over because too expensive. So it's justified. You're trying to use the minimum you can live with and still be within the codes and everything. And you want to know what the design temperature is, because you can't design any flexibility unless you know how much expansion you have. So, you know, the temperature is going to dictate how much flexibility we need. So you got to find out your design pressures, because part of the piping code, you have to design the system for the design temperature and design pressure. So you want to think about equipment, what kind of equipment you have, and what the allowables are there. So you got to keep all the things in mind before you start thinking about the stress analysis, and check what's the allowable stresses for the material you're working with. And not only that, you got to worry about the site conditions. Because see, on the north slope, site conditions are different. Your installation temperatures are different. Your winter temperatures are different. So you got to consider where this plant is going to be built. So you got to use the client information for that site. And that will tell you what kind of loads you have to consider. So this is the things a stress analyst has to think, keep in mind when doing the stress analysis. So now we got to get into the load definition. What that load definition is, we're going to talk about is the load, it's the forces. You can call it a force or you can call it a load. It's the same thing. Now, when we're working with the piping, if the pipes are cold, all you're going to have what? Just a dead weight. So the pipe is just sitting on the steel. All you have is a dead weight, which is called a primary load. We have primary load, we have a secondary load, and we have occasional loads. The three kind of loads has to be considered in any system, even for structural, or even for equipment. For everything we are dealing with piping, structure, equipment, you have to consider these loads here. That's what is a result of the piping system under operation. This is the final answer everybody looking for. Hey, after you design everything, what are the forces we had to worry about? Like I said, primary load is the dead weight of pipe, valve, insulation, flange, other mechanical loads. Anything which is just sitting there. It's just cold. If you got a flanges in the middle, you got a valve, pipe, it's just a dead lid. It's always going to be there, regardless you operate the plant or not. Those loads are considered primary. And secondary loads are when you operate the plant. That happens when the pipes start heating up and trying to bend the pipes, trying to put the forces on the sports, guides, nozzles. Those loads are called thermal loads. They're the thermal loads because they came due to temperature changes. So those are called secondary loads. They're going to be only there when there's a change in the temperature. Then we got the occasional loads. Those are loads are which they just happen suddenly, like an earthquake. You have an earthquake, you're going to have, or the wind, all of a sudden you got a gust of wind coming through, and you got those forces on the pipes, on the structure, on the equipment nozzles. Those called occasional loads. So these are the basic three loads we look for. And there are other factors causes more loads, but those are rare and in between, depending on the process system. We can look at those. Go ahead, John.
What's a PSV discharge?
Okay, PSV discharge is when you have a system, they want to relieve the pressure. Sometimes what happens is your pressure builds up in the system. They do not want that to increase. They set up your PSVs here that after that pressure they just blow open. They will release the pressure. And when they release the pressure, what happens is that you have a thrust force. Anytime you are exposing anything comes out of the system, go into the atmosphere, it causes a kickback. Like you guys see those shuttles coming and going. You don't hear much going, but coming when they come, you say boom. Same way as with this relief of these PSVs, when they are released excessive pressure in there, they make a boom noise and they have kickback. The force hits that backward and hits the pipe. Yeah. So those are considered, what we had there was a secondary, right? Yeah. Okay, let's get the load cases. The other load cases, we talked about thermal. Thermal is due to the temperature. Weight is due to the dead weight or any component there too. And the pressure load is due to the pressure inside the pipe. See, anytime you have pressure in the system, it creates a hoop stresses. It's trying to get out. You put the pressure, the walls are getting stressed out. Just like a balloon, when you blow into the balloon, it's getting bigger and bigger, the wall is getting all stressed out, getting thinner and thinner. Same way as the pressure loads are, pressure try to put hoop stresses in the walls of the pipe. Then we talked about the friction loads. Anytime pipe moves over this concrete structure or anything, is that dead weight trying to move, so something is restraining it back, trying to hold it back, which is a friction load. So to overcome that, before pipe can move, it has to overcome that force what the other member is trying to exert. So friction loads are due to the movement of the pipes overcome the dead weight. Then we got earthquake, which is seismic loads. We get wind loads due to the winds. Most of the sites, they're designed to 90 miles an hour wind. Some could be 100 miles an hour. It does not affect us too much if the pipes are low. But if your pipes are elevated, and you're 30 feet up in the air stuff, your wind loads could be pretty high. And the wind loads are proportional to the diameter of the pipe. The bigger the pipes, obviously, they're going to be more the loads. Slug flow loads. Slug flow loads are called when there is a condensate in the line, and then there is a pressure in the line behind it. It comes fast and carries the condensate with it, and it slams against the bend, against the elbow. So that we call it slug flow. It's just it's a force exerted by that pressure coming behind it. It tries to carry the slug with it, and wherever the turn, it hits it, and you got the slug forces. Pressure relief load, what we're talking about, the PSVs, when you release it to the atmosphere or any other media, due to the unbalance of the pressure, you're going to have this kind of load, pressure relief load. This is now. This is some more definitions of. Let me see. Okay, we have. I think we have the handout on that one, don't we? Yeah, what page was that? Page 10. Yeah, okay. So here's some more definition of a few things, like we talked about design pressure, design temperature. You all can, sometime you get a time, kind of go through them. There's another interesting kind of a point here. It's a 2.3 on page 10. It's called cold spring. What that is, this is a kind of no-no, but they used to use them in the piping systems, and still you can use it. What they do is, if the pipe is going 200 feet and they don't want to put expansion joint, they don't want to put expansion loop, what they do is, if the pipe is grown, let's say 2 inches, they will cut the pipe in the middle, ½ inch. If it's grown 1 inch, they will cut the pipe ½ inch, then they pull the pipe and weld it. So you have originally forced the pipe to come back this way. You have pulled it inward and they welded it. So now when it grows, it's trying to grow half, it cancels out the pull stresses, or relieve the stresses there. The only problem with this one is, if you ever had to rework that system, when you released it, it goes back to the other previous position. It's not going to go exactly the way you planned it. It's going to be loose. Now you're going to have pre-stressed nozzles and pre-stressed piping. So it's not recommended, and clients usually don't do that stuff. We used it about 20 years ago. I used it one time, but it's not recommended, cold springing. Then the definitions, ambient temperature. When somebody talks about ambient temperature, that means 70 degrees in the lower 40 states. In Alaska, up there, North Slope, is minus 50. Minus 50. No, that's 60, isn't it? Yeah, 60. Ambient is 60. But in winter, it's the minimum temperature, minus 50. But ambient will be 60 installation temperature. So what other terms are dead load? When they're talking about 2.5 dead load is strictly due to the weight, like we talked about it. Other terms, design temperature, design pressure. You know where we get them? Anybody knows where they come from? Design temperature, design pressure, they are from the line summaries. The process group provide those. And on the page 11, there are more definition of the loads and stuff, so you guys can look at later. You guys hear about what else we have. Okay, now we're talking about here what the stress analyst has to kind of watch for is allowable loads, how much they can load the structure. If your structure is designed to take care of only 5,000 and you can't have the 6,000 design loads, so you have to stay within the limits. And the same thing goes with the piping components and the machinery or any equipment. You got to stay within the allowable loads, and everything is given to us by the codes or the vendors or the structural engineers. So you have all the information which are not to exceed. Okay. Next one. And this is a formula here to calculate the allowable stress. It's expansion allowable. This is how we calculate in the code wise what the stress is allowable. These are we can exceed these equations. Okay.
So what is SH and SC?
This is a sustained allowable. This is what you get from the code for the material, what your allowable stress is. And for the seismic, they allow you to go 1.3 times higher, because they happen, occasionally, and that has nothing to do with the process. So for occasional loads, you can go 1.3 times. And up on the top is expansion allowable load. What's the total allowable? Is the combination of cold stresses and hot stresses. And longitudinal is stress due to pressure. It's a combination of those. This is your allowable. If you have those numbers, that will give you allowable stress you can have maximum. And those comes from the material. SH, HC, and SL you have calculated. Okay. Now again, that was a few comments about the stress loading and stuff there, but now actually we're talking about methods of pipe stress. How many ways we can do the pipe stress analysis. The number 1 and 2 and 3 were the only available a few years ago. I'm talking about 70s. They were not much into computer modeling, but now we got approximate methods. Now, when we talk about approximate methods, these are the charts what we had discussed in the beginning. This the approximate methods of page number 1 and 2 and 3 and 4 all the way up to page 6 or 7. Yeah. So if you have all those 7 pages there, and you have all the information here to do by approximate methods, you can do stress analysis. But that means you have the chart here that tells you how much total thermal deflection you're going to have in the system. So you have the delta, the total overall expansion or contraction in the system. And then we had a chart what tells us where's the diameter of the pipes are. And this tells you what the moment of inertia of the pipe is. And we know what the length of the pipe is. If we look at page 1, to the right on the top, and that will tell us what the force will be in the system, because E, you got E I delta. E is the elasticity of modulus of elasticity. Here, then I is the moment of inertia, and delta is your total growth. And you divide by 144, and LQ, L is your total length available to you for bending. So it's just simple formula here. You plug in that information, you got the force, and we will look at that sketch here when we get into the manual calculation. Will show where those forces are coming from. Page number 2, again, stress levels. We know our last Young modulus there. We have the diameter, we have the growth. We divide by 48 by length squared. So these formulas, there's 2 simple formulas you can use to get the stress and loads. These are called approximate methods. And you had to, what you used to do is you divide the piping system into smaller portions between the sports. You go sport to sport and figure out from next to next. So you break the system, or you can add up all the lengths together and calculate whatever the resultant length is in one particular direction. So these other methods allow us to take a center method. This is using the moment diagrams method. This involves some calculations. You've got to find the CG of the system. And then computer modeling is the best and easiest these days. And but before we do that, let's look at that page number 12 on that handout you guys have. So that demonstrates how we do manual calculations or approximation calculations using the same formula, which is equation 5-27. That equation, that's the same formula here, and all the variables are in those tables or the charts, and we can calculate the force. And in the same calculations, page number 13, rather 14, equation 5-35, that's for the stresses. And after that, there's examples with the numbers. So you can easily follow the example. They have fill out some numbers here, and you calculated the forces and stresses. So this is how calculations are done manually. Now we got 4 methods of doing the stress analysis. We basically use only 2, approximate method or the computer method. These days, that's all basically we do. Any small piping, which is called small bore piping, chord lines, we just do by inspection or by approximate methods. You don't have to waste time doing computer analysis. You can simply use the charts, and you can do the analysis on the chord lines and small lines. But anything hot and high temperature, high pressure lines, critical lines, we use computer modeling techniques. So this, John, go to the next one. So now this chart is we have created for our own company here. Most companies have the same way. This tells us you want to do a computer analysis, or you can do manual. That kind of allows you to follow the chart. Because in any kind of job, you got utility lines which are cold, gas lines, water lines. The client don't want you to waste time running computer analysis. They want to see, hey, which lines you're going to do with the computer. So because your budget is based on how much work you're going to do. The easier one you do, it takes less time by inspection, by the computer, it takes more time. Plus you have to do the documentation. Plus you have to provide the client with the calculations. If you do by inspection or by approximate methods, you don't have to give them the calculations. So this chart tells the stress analyst and the client that which lines we're going to be using which method to do the stress analysis. So this is the example I was going to show you guys here where those formulas are. You guys seen this one here, page 12, what it was? Yeah, page 12. So this is the same page. And it has the example, the equations, and examples in the back, so you guys can follow that. Right. Go ahead. You can skip these pages. Yeah. Okay. Now this is the real thing we were talking about. This is a lifesaver and the best software available in the industry. It's done by COAID out of Houston. I think they have worked on that software for the last 25 years or so. We haven't found any bugs, nothing. They use all over every country you talk to, any company, they use it. And it's a fairly expensive software. It runs for one seat, you're talking about $6,000 for every machine you want to run. So this is a pipe stress analysis software. They got other software for the equipment, for the tanks, but this is strictly for the pipe stress analysis. So what we'll do is we will go through it and see how it works. Now, let me kind of brief you guys up quickly before I get into this one is what is the overall process? How do all this information get together? How we collect all this stuff? The piping design group creates the piping system, and we get from them piping configuration. Anything for the temperature, pressure, and the commodities, all the stuff comes from the process group through the line summary. So we get a line summary from the process group, will give us all the conditions, and we get a client requirements about the site requirements for the climate, for the seismic, or the wind analysis. They're a criteria. And the materials, we get it from the material spec group. We get a material spec group. They use the materials which are recommended for a particular service, and they are approved by the client. So, and we use structure group to support the pipes. So we get all the information we collect, and then we go ahead start inputting. If you all look at this guy here, this is the page we input everything into it. And so far, you look here, we designate, did we have that ISO here? It's in the data, huh? Okay, we can show you that later. What we get is the piping isometrics. You guys familiar with the isometrics, what they look like? But you guys seen a layout system, right? They're showing you guys pipe stress, not a pipe stress, any isometric? Did they mention isometrics or no? Okay. So we get isometrics to do the stress analysis, and those isometrics are used for the fabrication too. They go for the fabricators to fabricate from those ISOs. We get the ISOs, and then we put the node points. In other words, we put the address on every component. Just like every street has a house number, this and that, the same way we designate to and from. So we break all the components of the piping system to input it. So in this case, we go in here, there are 4, John? So we're going from 4 to 3. So we're telling them we're going from this house to next house here, and the distance between that one is 4 feet, 10.5 inches. In what direction? It's a vertical. So piping systems are all oriented for the global axis. But the global axis, if you guys are not familiar, it will be like north-south. We call it the Z direction. East-west, we call X direction. Up-down, we call vertical direction, which is the Y. So here, pipe is going from